the first thing that we need to know technically is what do you exactly mean by transformation. So in the last class, we did see that by transformation, I simply mean that I'm going from one set of coordinate system to another set of coordinate system. Now, normally when you come across these kind of problems, you are usually simple generalized in nature. What we are doing in classical mechanics for the last 3 units is we are trying to generalize everything so that if we have a model, we can actually fix in any kind of situation that we have. Okay. So here also we are going to do it. So we are not giving away with the cyclic coordinate concept or the Lagrange or the Hamiltonian. Everything will be there, and then we are going to understand transformation in the light of Hamiltonian or Lagrangian equations. Okay. So what we do is, in general, if we are going to convert it from, let's say, polar coordinate to a Cartesian coordinate, you basically use this relation or you use this theta relation. Okay. So whenever you are having a transformation of, let's say, from one coordinate system, let's say small qj, which is generalized, to another set of coordinate system, let's say capital Qj, we basically call it as point transformation. And as I told you yesterday, point transformation is something which is more or less done in the configuration space. So you've just got x, y, z. So whenever there is a point transformation, I'm dealing with more of Lagrangian. But then, in reality, we are more interested in knowing what is the exact path that the system follows and so on. And as a result of which, we get help from Hamiltonian, where we also consider the momentum coordinates. Right? So we have got a system of 6 coordinates now, and we basically call it as the phase space. So whenever we are doing any kind of transformation, that means we are going from one set of coordinate system to another set of coordinate system in phase space, that is canonical transformation. So you have to remember this, that in this chapter, we are dealing with canonical transformation. We're not concerned about point transformations. Okay, so that's important. And since we are taking canonical transformation, we have to include momentum. The technique or the approach that we have has to be different. Okay, we have to consider all the parameters possible. So this is what we have seen in the last class. And if we basically consider Lagrange's equation of motion, and we consider the generalized coordinate here, let's say we have got ddt of del L del small qj dot minus del L del qj is equal to 0. This small qj dot, we replace it by capital Qj. Right? This small qj is, so any, okay, so the transformation that we'll usually have all will be written in terms of capital Qj and capital Pj. So that means if we say that small q and small p is the old set of coordinates, capital Q and capital P will represent the new set of coordinates. Okay, so this is something which is there. And accordingly, the Hamiltonian's equation also will change, and the form will be something like this. Qj dot is del H del Pj, and Pj dot is minus del H del Qj. That was the old form, right? And if we transfer it to the new form, we have got capital Q and capital P. So we replace it by capital Q, capital P, capital P, capital Q. Okay. But then, since we said that originally Hamiltonian was a function of only Q, P, and J, right? Q, P, and T, right? T I am not writing. But then the new Hamiltonian that we are talking about will be a function of capital Q and capital P. Okay. So that means that this also needs to be changed. So we have just written a new set of function. Okay. So that is there. And then we know that this capital K will represent a function of capital Q, capital P, and capital T, and it will be a substitute for the Hamiltonian. We've also seen, okay, I'm going fast because we have done it in the last class. Okay, for those who have not attended, you have to check the recording in the last class. We have also seen that if we use the Jacobi integral, we can actually write it down in this form. P Qj L dt equal to. But if this is valid for L, they should also be valid for H. Okay, so we can actually replace the substitutes here. So small p will become capital P, small qj dot will become capital Qj dot, and H can be represented as k. So this is the Jacobi integral we have. Now we have these, but that does not mean that this will be equal to this. Okay, that is not true. Okay, the total will be 0, but then you have to do the integration part. So for that, we are going to introduce another parameter. Okay, and what is that parameter? That parameter is something which we called it as f. Okay, so if we just write down this, one is in terms of k. So that was the new set of coordinates. Okay, capital P, capital Q, and capital K is new set of coordinates. Old set of coordinate we have got small p, small q, and h. That's the old set of coordinates. Okay, but for both the cases, the right hand side is 0. So what we can do is we can combine them together, and we can just write down the old set of coordinates minus the new set of coordinates, integrate it over the limit t1 to t2, okay, and dt is equal to 0. Okay, and then in Jacobi integral we have got this small variation.
So when you combine both of them, we have got this is equal to 0. Okay, so that is important. And this function, let's just take this new function. Okay, this is something which you have to understand totally separate. So we have got a function f, which is a function of small q, small p, and t. Okay, the old set of coordinates. And then if you basically consider it in terms of the Jacobi integral, please you can write it down in this way. Okay, you don't get confused here. We can always write it down in df dt of dt integration of t1 t2 in delta of that. Okay, so this t and this can get cancelled. I've got just integration of df, so it will be nothing but f. Okay, and we'll integrate it from t1 to t2, and then there is a variation delta. So if I do this calculation, okay, if I do this calculation and if I do the partial differentiation, at the end point, the variation is nil. The variation with respect to Q or with respect to P at the end point is 0. The question is how? I think I've explained it yesterday. Okay. What happens is at the end points, that is T1 and T2, the variation in QJ and PJ will vanish. Okay. It will vanish. Okay. There is no such variation. And as a result, what I can do is I can consider this part to be 0. Remember 0, not t is 0. Take this. What we can do is this simple. We already had this equation, this minus this of dt is equal to 0. There is no harm in adding an additional term df by dt, whose integration over t1 to t2 delta dt will give you 0 again. So even if I add it, I am not changing anything. Okay, I am not changing anything. So that's important. Okay. So what we can do now is, okay, what we can do now is we have got this function. Now this is possible. Now this is possible. What does it mean? That this part will be 0. Okay, we can just say that this entire thing is 0. And if that entire part is 0, that means this minus this will be df dt. This f is basically called the generating function. Okay, that's called the generating function, which is important. So what we are going to do is we are going to find out the different forms of generating function. How do we understand the different forms of generating function? You see this side. This is f. This can be a function of p, q, okay, q, or it can be a function of capital P, capital Q, and so on. Okay, it will definitely be have time as a factor also, because that can be a function of time as well. Okay, so we can have different forms of generating function, and this is what we are going to look into now. So the first bracket, okay, is basically a function of qj, pj, and t. Which first bracket? Check here. This one, this particular relation. Okay, this relation. Basically a function of small q, small p, and t, because Hamiltonian does have the factor of time. Okay. And then if you consider the second bracketed term, that is the new set of coordinates, it will be capital Q, capital P, and t, time. Okay. So what will be f a function of? So see this f that we're talking about can be any of the functions. Okay, it might have a number of variables involved. So the variables that are there are basically nothing but 4n plus 1. How? Because it can be a function of qj, pj, capital qj, capital pj, and time. So if there is a summation sign, if you can see this here, okay, there is a summation sign here. So this summation sign will actually represent that it will have n number of functions, okay, n number of variables there. So we can always consider that, okay. So just rub this off, okay. So we have this. Now what we do is, function, and a function of all the five parameters. It will not be, okay, because there has to be some dimensional correctness. So dimensional correctness, it will be a function of maximum three parameters, okay. So you can always combine them and then you can get that function. That is called the generating function, okay. So when we look into this, when we look into the generating function, we basically have f1 is a function of, can be a function of small q, capital Q, and t time. It can be a function of small q, capital P, and t. It can be a function of small p, capital Q, and t, or it can be a function of small p, capital P, and t. This is very important from your entrance exam point of view, okay. They do ask this question, okay. I have seen the question is one of the favorites, okay, in this particular unit, that they do ask some question from the generating function. So you have got four generating functions and you have to remember their form. That is what is important here. So what are the forms here? You basically have see, the time is common everywhere, okay. You don't need to really everywhere. Simply think about this. The first would be small q, capital Q, small q, capital P, small p, capital Q, small p, capital P. So they are the four generating functions that we have. Now the question is, if it's a generating function, it should have some kind of form, right? How does the function look like? And this is something which we are going to just look now. Okay. So this f is termed as the generating function and it has got four forms. Okay. And you need to remember all these four forms. Okay. You have to remember it also. That is very important. So let's take up the first form. The first form is small q, capital Q time. Okay. So if you look into equation 5, what is our equation 5 here? Okay. Let me just go back. So this is your equation 5. Okay. So if you look into equation 5, and if you say that it's a function of small q, capital Q, and t, we can easily differentiate it. Okay. We can easily differentiate it. And let's see how we can do it. Okay. So we can write down this particular equation as summation pj qj dot minus h. We'll take the new set of coordinates on the other side, pj qj dot minus k plus df1 dt q, capital Q, and t. And please remember, I've written it as df1. That means I'm finding out the form of the first generating function. We are going to take help from partial differentiation. Okay. So what we are going to do is this. If we just take f1 as the function, okay, and it's a function of small q, capital Q, and t, we can find out what is the total derivative. So if you want to find out the total derivative, you can just simply take each of these variables, right? So it is simple. I think this is something which you already know from your maths knowledge. First is with respect to small q, so del f1 del qj, okay, qj dot here, because this side we have got with respect to time, plus summation j del f1 del capital Qj into capital Qj dot, okay, plus del f1 del t. Okay. So this is the function that we have. What is our next step? Very simple. We are going to just replace it in equation 6, right? So can we replace it in 6? So let's replace it here. So see, we have replaced these terms. We have replaced these terms. Okay. And if you replace this term, you see something is common. What is common? See, there is a qj dot here, there is a qj dot here, right? There is a capital qj dot here, there is a capital qj dot here. So we can actually do the calculation, okay, and do the algebra and then just combine them together, okay. So what we are going to do is we have combined qj dot, okay, small qj dot, we have combined all the terms, and then we have combined capital qj dot, all the terms, okay, and then the rest of the term is here. Okay, so we have got three different parts. Okay, and I think you can guess from now here that all of them are independent of each other. If all of them are independent of each other, that means each of these should separately give you the answer to be zero. So this should be zero. Okay, this should be zero. Okay, and then this should also be equal to zero. So if we do it individually, all of them should separately give you zero. Okay, so that is important. So if we do that, what we can do is we can just write it down in this way. Okay, so if so an important point that you should write down in your exam is that this small qj and capital Qj are treated to be independent. Okay, this independent is the highlighted term. Okay, so this independent is the highlighted term. Okay, so this is important. So if we just take this, okay, independent term, then we can always write it down separately. So if we write it down separately, we can simply write it down as Pj is del F1 del Qj. Okay, how? Because if you go into that equation, back into that equation, you see this here. Pj is del F1 del Qj. Okay, so this is the first form of the generating function. Can we go for the next term, which is nothing but capital Qj will be minus del F del Qj. So you see, for a direct question that might be asked in your exam, they will give you the form of the function. Okay, they will give you the form of f1. Okay, and then you have to just differentiate it. Okay, and then find out what is the relation capital Pj or Pj. And so it will make you more clear. Okay, so right now we're just dealing with the general form, and then finally what we have is the relation between the new set of coordinates with the old set of coordinates. This is the relation. Okay. So if we basically solve this, okay, if we basically solve this equation 8, you see this equation 8, if we just solve it, see here, this side will be having a function having small q, capital Q and T, and this side will be having, so we can always do and rearrange it in such a way so that this capital Q can be on one side, okay, and the other terms, okay, that means Q, P and T will be on the other side. All these terms will be on the other side. So I can always rearrange that, okay, and then I can actually get the form of this. So this is something which you will get generalized, and this is also something which you will get, okay. And the final equation, that is the relation between uh, the k and h. It is basically nothing but the connection between the old and the new Hamiltonian. And what is this 11 and 12? 11 and 12 are called the transformation equation. Okay, so if we just look into this 11 and 12, I think this is important. So please just let me just keep this everything on screen. Okay, so you see these are the transformation equation. This is one transformation equation. Okay, and this is another transformation, and both of them are important. Okay, and this is something which we are going to deal with when you come across your questions. Okay, so I am going to give you some numerical problems and we are going to solve it together in the class, and this will actually help you out to understand it better. Okay, so I'm not going to proceed because I'm going to give you a task now. What is your task? You use the same now. Okay, whatever approach I have used now. Okay, and then of course you can go back here and you check the forms now. So see, this is the one we have done, right? So this is left. This is the second form. Just find out what will be the second form. Just find out what will be this form, okay? And then also find out what will be this form. Try to find out all the three forms, okay? And then if you do it once on your own, you can go from any generating function to any generating function. It will be more easy for you. So good practice, okay?